All right, buckle up, everybody, because today we are going deep, really deep into something we all experience every single day, light. And here's the kicker, we aren't just skimming the surface. We're going way past the basic stuff, the kind of things you learned in high school science class,
Right, we're talking about the truly mind-bending reality of how light actually works.
Exactly. We're diving deep into a YouTube video. It's called How Does Light Actually Work? And it's from a channel called History of the Universe, which is, by the way, a fantastic channel. I highly recommend it.
Oh, absolutely. They do a great job of making complex topics accessible and engaging.
And light is definitely a complex topic, even though, like I said, it's something we experience constantly, right? I mean, we literally couldn't see without it. But this video, I'll tell you, it made me realize just how much I didn't know about light.
It's really one of those things where the more you learn, the more you realize there is to learn.
100%. So where do we even begin? Well, the video starts us off at the very beginning, the Big Bang. Now, I always kind of assumed that, light was just there from the get-go. I mean, it's the universe, right? Everything all at once. But as it turns out, I was way off.
Yeah, it's actually pretty fascinating. In those very first moments after the Big Bang, the universe was incredibly hot and dense. Imagine this chaotic soup of particles just zipping around at unimaginable speeds.
Okay, so far so good.
Yeah.
Chaotic soup of particles, got it. But how does light fit into all of this? Or rather, how does it not fit in since it wasn't there yet, apparently?
It all comes down to atoms. See, in that early universe, it was just too hot and energetic for atoms to form. Electrons and protons, they just couldn't stick together.
Ah, okay.
Yeah.
So no atoms, no light.
You got it. It took about 400,000 years for things to cool down enough for those first hydrogen atoms to form, with their electrons finally bound to their protons. And when that happened, that's when light burst onto the scene.
Whoa, 400,000 years. That's like a really long time to wait for a light show.
It's practically an eternity in cosmological terms. But that first light, it was a big deal. It was made of photons, those fundamental particles of light. And those photons, get this, they've been traveling through the cosmos ever since.
Okay, wait a minute. So that starlight we see at night, those photons hitting our eyes, some of them could be billions of years old.
It's mind-boggling, isn't it? Think about the journey those photons have taken across vast stretches of space and time just to end up in our eyes.
It really puts things into perspective, doesn't it? The sheer scale of the universe and the incredible story that light tells. But okay, let's rewind a bit. Before we were talking about, the Big Bang and all that cosmic stuff. But how did people even begin to understand light? Way back when? I mean, did they even know it was light like we understand it today?
Well, the video mentions how ancient Greek thinkers had some pretty interesting ideas about light. Believe it or not, they actually thought that light emanated from our eyes. Like our eyes were sending out beams of light that allowed us...
Wait, seriously? Like our eyes were like little flashlights? That's kind of a wild concept.
It sounds strange to us now, right? But it shows how our understanding of the world evolves over time. Of course, they eventually realized that this idea didn't quite explain everything, like why we need torches to see in the dark.
Yeah, good point. Okay, so if it wasn't beams shooting out of our eyes, how did we get from there to, well, whatever it is we think we know about light today?
It was a gradual process, with a lot of brilliant minds contributing along the way. For instance, during the Islamic Golden Age, scholars made huge advances in understanding things like reflection and the power of lenses. And this laid the groundwork for later breakthroughs in optics and our understanding of how light behaves.
So it's like each discovery built upon the last. It's like a puzzle slowly being pieced together over centuries.
Precisely. And speaking of piecing together puzzles, that brings us to two of the biggest names in the history of science, Isaac Newton and Robert Hooke.
Oh yeah, these guys. Now, they weren't exactly the best of friends, right? More like rivals.
Let's just say they had a rather spirited debate about the nature of light. Both of them were brilliant, but they had very different ideas about what light was actually. Newton, he was convinced that light was made of tiny particles called corpuscles.
Corpuscles, so like little bullets of light.
Exactly. And that model actually explained a lot of things, like how light travels in straight lines, how it bounces off surfaces, things like that.
Yeah, I can see how that makes sense. It's intuitive, right? Little particles zipping through space.
Right, but Hooke, he wasn't buying it. He was vehemently opposed to Newton's corpuscular theory. He argued that light had to be a wave, like ripples on water, because of things like refraction. You know how light bends when it passes from air into water.
Oh yeah, I remember learning about refraction.
Yeah.
That's why a straw looks bent when you stick it in a glass of water.
Ah!
So wait, how could those tiny light bullets bend like that?
That was Hooke's point. It's hard to picture particles behaving that way. He thought it made much more sense if light was a wave spreading out and bending around obstacles. So who won this epic battle of scientific titans? Well, Newton's influence was so strong that his particle theory actually dominated for quite a while.
Wow, so even though Hooke had a good point about the bending light thing, Newton's idea still won out.
For a time, yeah. But the story doesn't end there. In the 19th century, a scientist named Thomas Young conducted his now famous double-slit experiment. Basically, he shone light through two tiny slits and looked at the pattern it created on a screen.
I vaguely remember this from high school physics, something about interference patterns.
That's it. What Young saw on the screen wasn't what you'd expect if light was just a stream of particles. He saw an interference pattern with bright and dark bands where the light waves overlapped and either reinforced or canceled each other out.
So like waves in a pond where they crest and trough, creating bigger waves or canceling each other out completely?
Exactly. It's a classic wave phenomenon. And this experiment was a huge deal. It really challenged Newton's particle theory and provided strong evidence that light was, in fact, a wave.
Okay, so case closed, right? Light is a wave, mystery solved. End of story.
Well, if only it were that simple. As I said, the universe loves to keep us on our toes. And just when scientists thought they had light figured out, along came another brilliant mind, James Clerk Maxwell.
Oh boy, I'm sensing a plot twist here. Who was this Maxwell guy and what did he do to shake things up?
Maxwell was a Scottish physicist, and he did some groundbreaking work on electricity and magnetism. He came up with these incredible equations, now known as Maxwell's equations, that unified electricity and magnetism, showing that they were actually two sides of the same coin.
Two sides of the same coin, so like they're interconnected somehow.
Exactly, but here's where it gets really interesting. These equations, they predicted the existence of electromagnetic waves. And guess what? Light turned out to be one of them.
Hold on, back up a second. Electromagnetic waves. So light isn't just any old wave, it's an electromagnetic wave. But what does that actually mean? I'm kind of lost now.
No worries, it's a big leap. What Maxwell's equations showed was that light is made of oscillating electric and magnetic fields, traveling through space at, you guessed it, the speed of light.
So these fields, they're like invisible forces that are constantly vibrating and creating these waves. And that's light.
You got it. And here's where it gets even crazier. His equations predicted that there were electromagnetic waves beyond what we can see, things like radio waves and X.
Whoa, wait, hold up. So you're telling me there's a whole world of invisible light out there that we can't even see?
You got it. That was a revolutionary insight, and it led to some incredible inventions like, well, the radio.
The radio. So like Maxwell's equations, they're the reason we can listen to music and podcasts.
Pretty much. It was thanks to pioneers like Guglielmo Marconi who used Maxwell's theories to figure out how to send messages wirelessly through the air using radio waves.
Wow, so we have Maxwell to thank for everything from like AM radio to Wi-Fi.
You could say that. His work was a major turning point in our understanding of light and electromagnetism, and it paved the way for a whole host of technological advancements that we rely on.
This is incredible. So we've gone from thinking light shoots out of our eyes to realizing it's this wave of electric and magnetic fields, all thanks to the work of some truly brilliant minds.
It's an amazing journey of scientific discovery, isn't it? And it's a reminder of how much we still have to learn about the universe.
Okay, so at this point, we've established that light is an electromagnetic wave. Case closed, right?
You would think so, wouldn't you? But as I mentioned earlier, the universe loves to keep us guessing. And light, well, it still has a few more tricks up its sleeve.
Oh, no, there's more. This is already blowing my mind. All right, I'm ready for the next chapter of this story.
Okay.
So where were we? Oh, yeah, light. It's an electromagnetic wave. That's it. End of story. Mystery solved. Or is it?
You'd think so, right? I mean, it's a pretty elegant explanation. But the universe, well, let's just say it has a knack for throwing curveballs our way. And in the case of light, that curveball came in the form of something called the photoelectric effect.
The photoelectric effect, huh? All right, lay it on me.
Yeah.
What is this photoelectric effect, and why does it mess with our nice and tidy wave theory of light?
Well, think back to what we were talking about earlier. Light as an electromagnetic wave, right? These oscillating electric and magnetic fields carrying energy through space.
Yeah, I remember. And it's traveling at the speed of light, which is like the ultimate speed limit in the universe.
Exactly. So scientists, they were doing experiments shining light on different materials, and they noticed something really strange.
Strange in a good way or a bad way? Like, oh, cool, that's unexpected, strange, or uh-oh, this breaks everything. Strange.
Definitely the, this breaks everything kind of strange. They found that when they shone light on certain materials, it caused electrons to be emitted from those materials. And that wasn't too surprising in itself.
Okay, so light hits stuff and knocks electrons loose. That makes sense, right? I mean, light carries energy, so some of that energy could be transferred to the electron, giving them enough oomph to escape.
You're on the right track. But here's the thing that didn't make sense. The color of the light mattered a lot. And I don't mean like, oh, it looks pretty or anything. I mean, it made a fundamental difference in whether electrons were emitted.
So what do you mean? Like shining a red light versus a blue light, it would change whether or not those electrons popped off?
Exactly. If light was just this continuous wave carrying energy, you'd think that any color of light would eventually cause electrons to be emitted. Just shine it long enough, and those electrons would absorb enough energy to break free.
Yeah, that's what I would have thought too. More light, more energy, more electrons getting knocked loose, regardless of the color.
But that's not what they found. They saw that shining blue light on a material would cause electrons to be emitted right away. But shining red light, no matter how intense it was, didn't cause any electrons to be emitted at all.
Okay, so something's fishy here. It's like the light was delivering its energy in these little bursts, these little packets, instead of this continuous wave.
You're getting it. It's like instead of a steady stream of water, it was more like someone throwing tiny water balloons at the material. And if the water balloons weren't big enough, they just wouldn't have enough force to knock those electrons loose.
Wait a minute, little packets of light? Didn't Newton have an idea like that way back when, with those corpuscles he was so fond of?
You're exactly right. And that's where our old friend Albert Einstein enters the picture.
Einstein, like the EMC guy.
That's the one. In 1905, the same year he published his theory of special relativity, he also came up with a revolutionary idea to explain the photoelectric effect.
Okay, I'm intrigued. What did Einstein propose? Did he have a eureka moment while working on relativity and was like, oh, and by the way, I also figured out light?
Kind of. He realized that light energy, it wasn't continuous, it was actually quantized. It came in these discrete packets, these little bundles of energy, which later came known as, you guessed it, photons.
So light is a particle, after all. I thought we settled that debate back in the 19th century with Young and his double-slit experiment.
It's not that simple. It's not like we can just throw out the wave theory. Light does exhibit wave-like behavior, but Einstein's explanation of the photoelectric effect showed that light also has this particle-like nature.
So it's both a wave and a particle. But how is that even possible? That doesn't make any sense.
I know, it's a real head-scratcher, isn't it? It turns out that light doesn't fit neatly into our classical categories of wave or particle. It can behave like either, depending on how we're observing it or interacting with it.
So reality's fuzzy. It all depends on how you look at it. This quantum stuff is seriously messing with my brain. But let's get back to these photons. They're like little bundles of energy, right?
Yeah.
But the video mentioned something about light actually being able to push things. How does that even work? Light doesn't have any mass, does it?
It's true. Light is massless, but it does carry energy and momentum. Think of it this way. Can't get knocked over by a beam of light, but you can feel the warmth of sunlight on your skin. That warmth is a transfer of energy. And even though photons don't have mass, they can still exert a tiny amount of pressure.
Okay, I think I'm starting to get it. So like those futuristic solar sail spaceships I heard about where they use sunlight to propel themselves through space.
Yeah.
That's actually a real thing, not just science fiction.
Not science fiction at all. There have already been several successful demonstrations of solar sails, small spacecraft using large reflective sails to capture the momentum of sunlight and navigate through space. Pretty amazing, really.
It is. So these photons, they're pretty powerful little bundles of energy, even without any mass. But this idea that light is both a wave and a particle, how does that actually play out on a practical level? Like, how do photons interact with matter?
That's where we need to go beyond classical physics and enter the realm of quantum field theory.
Quantum field theory. Uh-oh, are we getting into the really deep end of the pool now?
Yeah. Don't worry, I won't drown you in equation. The basic idea is that everything, light, electrons, everything we think of as particles, are actually excitations of quantum fields.
Excitations of quantum fields. I'm not sure that's making it any clearer. Can you break that down a bit more?
Imagine a vast, invisible ocean that stretches across all of space and time. This ocean is the quantum, and particles like electrons and photons are like ripples or disturbances.
So instead of these tiny billiard ball-like particles zipping around, we have these fields that are constantly rippling and creating waves.
That's a great way to visualize it. So light, it's a ripple in the electromagnetic field, while an electron is a ripple in the electron. And the way these fields interact with each other, well, that's where things get really interesting.
Okay, I'm ready. How do they interact?
They interact by exchanging particles. It might seem counterintuitive, but in the quantum world, that's how force...
Wait, hold on. Exchanging particles. But I thought we were talking about field.
I know. It's a lot to wrap your head around. But, for example, the electromagnetic force between two electrons, it's actually mediated by the exchange of photons.
Seriously. So the force that holds atoms together, that's actually due to particles of light being passed back and forth between electrons. That is just bonkers.
It is, but that's the beauty of quantum mechanics. It's full of these mind-bending concepts that challenge our everyday intuition. And one of the best ways to visualize these interactions is using something called Feynman diagrams.
Feynman diagrams. I think I've seen those before. They're like little squiggly lines and arrows, right?
That's right. Feynman diagrams are like a shorthand for representing how particles move and interact in the quantum world. They were developed by a physicist named Richard Feynman, who had a real knack for explaining complex things in simple ways.
So they're like a comic strip for quantum physics. I can dig it. But how do they actually help us understand how light interacts with matter?
Well, imagine you have two electrons approaching each other. The Feynman diagram would show them exchanging a photon, and it's that exchange of photons that creates the electromagnetic force between them. It's like they're playing catch with particles of light.
Okay, I think I'm starting to see the picture here. So light, it's not just something we see. It's this fundamental force carrier that's holding the universe together at the smallest level. But the video mentioned something else that was pretty out there, something called the transactional interpretation of quantum mechanics.
Ah, yes, the transactional interpretation. That one's a real doozy. It's a way of thinking about how particles interact that involves, well, time travel.
Time travel. Hold up. Are we going down the rabbit hole here? Are we talking about photons hopping through wormholes or something?
It's not quite that dramatic, but it is pretty mind-blowing. The transactional interpretation suggests that when two particles, like our electrons, exchange a photon, they're actually sending a message back and forth through time to agree on the exchange.
A message through time. So, like, the future is influencing the past. My head is spinning.
I know, it sounds crazy, but the transactional interpretation, while it's still being debated, offers this really interesting way to visualize how these quantum interactions could be happening outside of our normal understanding of time and causality.
Okay, so time is even weirder than I thought. But let's stick with these photons for a minute. We've talked about how they're created, how they interact with matter, how they mediate forces. But what's it like from the photons' point of view? Do they even experience time at all?
That's a fascinating question. And it brings us back to Einstein and his theory of special relativity. One of the key principles of special relativity is that the speed of light is constant for all observers. No matter how fast you're moving, light will always appear to be traveling at the same speed relative.
Right, the cosmic speed limit. Nothing can go faster than light. But how does that tie into a photon's experience of time?
Well, here's where things get really trippy. For something traveling at the speed of light, like a photon, time essentially stops.
Hold up. Time stops. So from a photon's perspective, it's born and then instantly absorbed, regardless of how far it's traveled. Like, it could journey across billions of light years, but it wouldn't experience any time past.
You got it. It's almost like the universe is a flip book, and a photon is only experiencing a single page. It doesn't experience any journey or passage of time the way we do.
That is wild. So all those billions of years of cosmic evolution, galaxies forming, stars exploding, it's all just one snapshot from the photon's perspective.
That's the mind-blowing implication of special relativity. It really challenges our everyday intuition about time and space and makes you wonder about the true nature of reality itself.
I'm definitely wondering. So are we done with light yet? Or does this wild ride have any more twists and turns? Okay, so we've gone deep into the quantum world. We've talked about photons, fields, Feynman diagrams, and even time travel. But I still have one big question. If a photon doesn't experience time, does that actually affect anything on a larger scale, like out there in the universe, not just at the subatomic level?
It absolutely does. Remember when we were talking about Einstein's theory of special relativity? Well, he also developed another groundbreaking theory called general relativity, and it deals with gravity.
Oh, yeah, general relativity. That's the one about how gravity isn't really a force. It's more like the curvature of space-time.
Exactly. And one of the key insights of general relativity is that massive objects like stars and galaxies, they actually warp the fabric of space-time around them.
Warp space-time. Okay, I'm trying to wrap my head around that. So space-time isn't just this empty, static background. It's like a flexible sheet that can be bent and stretched.
That's a good analogy. Think of it like a trampoline. If you put a bowling ball in the center, it creates a dip, right?
Right. The trampoline curves downward around the bowling ball. Okay, so massive objects do the same thing to space-time. They create these gravity wells that curve the fabric of space and time around them.
Exactly. And the thing is, even though light is massless, it's still affected by this warping of space-time. It's not that light is being pulled by gravity in the traditional sense. Instead, it's simply following the curves in space-time that are created by these massive objects.
So light bends. Wow, that is wild. But does this bending have any observable effects? Or is it just a theoretical thing?
It definitely has observable effects. One of the coolest is something called gravitational lensing.
Gravitational lensing. I think I've heard of that. It's how astronomers can see things that are really far away, right?
You got it. Imagine a distant galaxy way out there in the universe, Located behind a massive cluster of galaxies that's closer to us. The light from that distant galaxy has to travel through the warped space-time around the galaxy cluster in order to reach us.
Okay, I'm trying to visualize this. So the light from that faraway galaxy, it gets bent as it passes by the cluster, like it curves around it.
Precisely. And because of that bending, the light from that distant galaxy can actually appear distorted and magnified to us as if we were looking through a giant cosmic lens.
Ah, I see. So that's why it's called gravitational lensing. The galaxy cluster acts like a giant lens in space, bending and magnifying the light from the objects behind it. I think I've seen pictures of this, those incredible images from the Hubble Space Telescope where galaxies look all stretched out and warped into arcs and rings.
Those are prime examples of gravitational lensing. It's not just a cool visual effect, though. Gravitational lensing is a really powerful tool for astronomers.
In what way? What can we learn from looking at these warped images?
Well, for one, it lets us study objects that would otherwise be too faint or distant. But it also helps us map the distribution of mass in the universe, including this mysterious stuff called dark matter.
Dark matter. The invisible stuff that we know must be out there because of its gravitational effects, but we still haven't directly observed it.
That's right. Gravitational lensing is one of the main ways to study dark matter and trying to figure out what it's made of. We can see how it bends light from distant galaxies and use that to map it.
That's so cool. So light isn't just illuminating the universe, it's also helping us understand its hidden structure. I feel like we've learned so much in this deep dive, from the birth of photons and the Big Bang to the mind-bending implications of quantum field theory and relativity.
It's a really remarkable journey, isn't it? And it highlights just how amazing and mysterious light really is. It's something we encounter every single day, but it holds these deep secrets about the nature of the universe.
Absolutely. So after all this, what's the one big takeaway about light that I should remember? What's the biggest lesson?
That's a tough one. I think the most important thing to remember about light is that it constantly challenges our assumptions. Over the centuries, it has forced us to rethink our understanding of from the nature of space and time to the very building blocks of matter.
You're right. Light is definitely full of surprises.
Yeah.
It's a reminder that there's still so much we don't know and so much left to discover.
Exactly. And that's what makes science so exciting. We're constantly pushing the boundaries of knowledge and uncovering new mysteries.
I love that. Well, on that note, I want to thank you for joining me on this incredible journey into the world of light. And to all our listeners out there, keep those minds curious and those questions coming. We'll see you next time for another deep dive.